In this lesson, we shall focus on physics, grade 12, electric circuits, past exam questions, and a lot more. And we begin as follows. Right, question 8 must be started on a new page. A battery with unknown EMF and unknown internal resistance R is actually connected to 3 resistors, a high resistance voltmeter, 2 switches, 2 ammeters. You have switch 1, switch 2, 2 ammeters, ammeter 1, ammeter 2, of negligible resistance as shown below. State Ohm's law in words. State Ohm's law in words. Let us look at the statement of Ohm's law. I know that this is a law that you know very well, and we state the law as follows. And we say, in an attempt to answer question 8.1, we say the potential difference. Right, the potential difference across a conductor, right, across a conductor is directly proportional right to the current in the conductor at constant temperature. At constant temperature, in brackets, provided all other physical conditions remain constant. Remain constant. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature, provided all other physical conditions remain constant. In other words, we are saying the potential difference V across a conductor is directly proportional to the current I in the conductor, but you note that this potential difference is potential difference across the conductor and is directly proportional to the current in the conductor at constant temperature, provided all other physical conditions remain constant. So this is called Ohm's law in words. We move forward. In the next question, still a battery with unknown EMF E and unknown internal resistance R is connected to 3 resistors, a high resistance voltmeter, 2 switches, 2 ammeters of negligible resistance as shown below. You have the 2 switches, switch 1, switch 2, ammeter 1, ammeter 2, but also you have a high resistance voltmeter. So we can actually be in the position to see a voltmeter here, but this one is not a standard voltmeter, but it is a high resistance voltmeter. Good. Good. Let's perform some calculations here. Calculate the voltmeter. Calculate rather the reading on the voltmeter. Calculate the reading on the voltmeter. There is the voltmeter. So we want to find the reading on the voltmeter. But what do we know? We have knowledge of the other variables that exist in this case. And so what are the variables that exist in this case? Because we know that at this point, for example, the total current that passes through, or the current that passes through ammeter 1, yes, it's 1,5 amperes, meaning the resistance is V over I. And therefore, at this point, what then exactly do we know? If we want to find the reading on the voltmeter, right, and the voltmeter is the voltmeter V. So we know that Ohm's law states that R equals V over I. Then the question becomes, what is the reading on the voltmeter? So we are interested in the reading on the voltmeter. But the question becomes, what is the resistance? Right, what then do we regard as the resistance here? If we already know that the reading on the ammeter A1 is 1.5 amperes. So we know very well that here, the current that passes through, because this is positive negative, it's 1.5 amperes here. And obviously we agree that there's some other current that is going to pass through the other side. Okay. And so now, at this point, you need to reason this out. You need to reason this out. So thinking of this, you need to realize a couple of things. That there are a couple of ways to actually reason this. For example, somebody can consider the current that goes through here in this resistance here to be in a position, for example, to find the potential difference here. Right, so which I think is going to be the easiest way to do the question. But simultaneously, what you need to consider also is that this particular resistance here and this resistance here give us the R in series. R for the series combination would be 2 ohms plus 5 ohms. Yeah, can write like that. You can write R1, R2. 2 ohms plus 5 ohms. And this gives us exactly 7 ohms. Meaning here you're going to have exactly 7 ohms. Okay. And if this is the case, you're going to use this formula. If R is V on I, what is R? It is 7. V over 1.5. Okay, this is one way. So V is going to be 1,5 times 7. And then we need to get the answer out of this. Let's launch our calculator. So you have 1.5 times 7. 10.5. 10.5 volts. 10.5 volts. 10.5 volts. Any question? Okay. Now, this is okay, good. Excellent stuff. I'm glad that you're able to get it right. Okay, because we used this here with the understanding that if these two, this and that, are parallel to each other, then the potential difference here and there is the same. So we found the potential difference here. It is the same as the potential difference there, which would be the potential difference in the voltmeter or across the voltmeter. Some of the questions I'm going to give to you to try. Now, I want to find a reading on the ammeter A2 now. This one here. So the current is going to actually come like this. Right. Okay, let's continue. Let's continue. Okay, let's continue now. We'll look at the next one. Let's look at 8.2.2. Reading on ammeter A2. The reading on ammeter A2. Now we want to know the reading here. What do you think the reading there is? I'm giving you 1 minute, then we shall discuss it together. Or like 2 minutes. I'm giving you like 2 minutes. Okay, thank you so much. That's okay. You can just send the answer, then we shall do it together and be in a position to determine that. So now, at this point, obviously, we understand something, that you have the positive here and the negative. So that we have R equals V over I. So in the end, you have the resistance. And want to find there is the actual current through I2, or rather A2. So what then we can be able to do, we can actually first determine the electrical current, which means I is V over R. I becomes V over R. What is the potential difference here? We've already found the potential difference to be 10.5 volts. 10.5 volts. Ten 10.5 volts. Divided by the resistance. And then if it's 10.5 volts, then we just need to know the current that is through there. So we can know here it is actually exactly, okay, we need the resistance, which is exactly 3 ohms. And divide this here. Right, so dividing this would therefore mean that you have 10.5 divided by 3. Okay, yeah, 3.5. 3.5 amperes. So I total. So now there's going to be I total because here we know it is 1.5. Okay, good. How did you get 3? Okay, because we already know that the potential difference here is 10.5 volts across this particular conductor. And that will be the voltmeter reading here on this high resistance voltmeter. And then now we know that the resistance here, can write like this, is actually exactly 3 ohms. So that in the end, we have this here, the 10.5 volts and the 3 ohms. But VI equals V over R, which means that you're going to have exactly this. The 10.5 divided by 3, which is 3.5. So there's going to be I total, 1.5 amperes. And through this here, it's going to be exactly 3.5 amperes. So you have a 3.5 that combines with the 1.5 amperes, and they combine together, giving us 1.5, 3.5, which is 5 amperes. So that indeed it is exactly 5 because we're adding the 3.5 and the 1.5 amperes there. Right, the next question is to calculate the power dissipated in the 3 ohm resistor. So we want to find the power dissipated in the 3 ohm resistor. It's 3 marks. I'm giving you exactly 2 minutes. 2 minutes. All right, so let us continue to determine that one. So to actually obviously determine the power dissipated in the 3 ohm resistor, you would have exactly the following. To find the power dissipated, we already know that power, it's V squared over R. And so if power is V squared over R, but we want the power dissipated in the 3 ohm resistor, which is this one. Here we already know the potential difference is 10.5 volts. Which is 3.5 amperes. Which is, yeah. So, which means therefore, and the resistance is exactly 3 ohms. So you're going to have exactly the potential difference V, which is 10.5. You square that divided by the resistance, which is exactly 3, and we're going to use our calculator. We're going to use exactly our calculator and obtain the following. So this is going to be 10.5 which is 36.75. 36.75 watts. So P equals VI. 10.5 volts. Okay, in other words, you can use the top one or the bottom method. Right, in the case of the bottom method, you use power equals VI. And therefore, you know that the potential difference is 10.5 volts and the current through this one is 3.5 amperes. We use our calculator to verify the answer we're getting. So that is going to be exactly 10.5 times 3.5. And that is 36.75 watts. 36.75 watts. 36.75 watts. 36.75 watts. We continue. We continue. Right, we try the next one. Okay, but before we try that, I wanted to comment on the power relations, the power formulas. If power is VI, and we have knowledge of the fact that, for instance, R is V over I. That's what we know. And then we can say I is V over R. Moreover, we can say V is IR. Okay, these are the Ohm's law relations. Plugging them in here, if I, for instance, is V over R, V by V becomes V squared over R. Okay. Power is potential difference by current. Now, let's just discuss this one. What is potential difference? It's IR times I squared R. I squared R. Power is V squared over R. I squared R. VI. So we have sort of established these three relations. Power is VI. Power is V squared over R. Power is I squared R. Okay, so yeah, just take a look at these relations and make sure you understand them. And make sure you understand them. Okay, we'll move forward to the next question. Right, so switch S1 is now opened. So switch S1 is now opened. So it's like this. Switch S1 is now opened. Switch S1 is now opened while switch S2 remains closed. Switch S2 remains closed. The reading on the ammeter A2 is now 3,64 amperes. It's now 3,64 amperes. Okay. Calculate the EMF of the battery. I'm giving you 2 minutes. I'm giving you 2 minutes. Let me know when you're done. Please. Let me know when you're done. Okay. Okay, yeah, please let me know when you're done. Um, right, right. Okay, yeah, please let me know when you're done. So, okay. Okay, let me know, please, when you're done. Okay, let me know, please, when you're done. Yeah, you sent the answer. Okay, so, please let me know when you're done. Right. Please let me know when you're done. Um, okay. Um, right. Right, how far? Okay, let me check. Let me see. Okay, that's fine. I'm giving you some time. We're not running. We're not in a hurry, but we're interested in um we're interested in making sure that every single bit of thing is okay. Right. Right. Okay. Okay, yeah, so you let me know when you're done. Because I want us to practice a little bit, not just, um writing out, but we need to practice. Right, 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 right. Um, right. Okay, yeah, we're practicing. I want to see what you're gonna do because we're practicing to make sure you have a fair chance to do the question. And then obviously we'll see then what to do. We'll then see what to do. Um, so we then have the following, yeah? So now, right, right. So you let me know when you're done. Let me know when you're done. Okay, right. Let me see. Okay, that's fine. Remember, the aim is not to torment you, it's not to torture you, for practicing and trying the things, but the aim is to cultivate the skill and the ability. So let us look at 8.3. Right. Continue. We continue. So this battery now with EMF E and unknown internal resistance R is connected to three resistors, a high resistance voltmeter, two switches, S1, S2, and two ammeters of negligible resistance as shown below. Switch S1 is now opened, while switch S2 remains closed. The reading on ammeter A2 is now 3,64 amperes. Calculate the EMF of the battery. So we proceed as follows with this particular question. We proceed as follows. Now, the couple of things you need to take into account here, but it is the fact that we have already done some calculations. For example, we have determined that here this is 10,5 volts, this is 3,5 amperes. Here it is 3,5 amperes, 1,5 amperes, potential difference, it's 10,5 volts. So, all right. So these are the things we already know. But now, what then do we do here? So to be in a position to deal with this, we will look at the fact that we want to find the EMF of the battery. But the formula for the EMF of the battery, E equals I, in parentheses, R plus R. One over R parallel. It's 1 over R1 plus 1 over R2. 1 over R parallel. It's 1 over R1, which is 1 over 7. Because here it is exactly 2 plus 5, which is 7. It's exactly 2 plus 5, which gives us a 7. So we're going to have 1 over 7, 1 over 3. And therefore, the 1 over R parallel is 21 here. 3 plus 7, giving us 10 out of 21. Which is 21 divided by 10, 2.1 ohms. Now, it means therefore, but you can do it like this, but you can do it different as well. I mean, you can say the R parallel becomes R1, R2 divided by R1 plus R2. This is another formula. You can do it like this for the parallel combination, 1 over R1, 1 over R2, or you can say R1, R2 over R1 plus R2. And to test this method, you'd say, for instance, R1, we call it 7 ohms. It's going to be 7 ohms times 3 ohms, which is the 7 ohms and the 3 ohms. 7 plus 3, 7 by 3 is 21 out of 10, which is 2.1 ohms. 2.1 ohms. So now, in other words, for S1 and S2 closed, we have the following. What then is the current for the EMF? You have already seen that this one is 1,5 and 3,5. And if we add them together, you get actually 5 amperes. The 5 is 1,5 amperes plus 3,5 amperes, which gives us 5 amperes, like so. Now, we want to find the EMF. So what is the resistance of the external circuit? External circuit. We've seen 2.1, which is the equivalent resistance of all the external components. Right, so it's actually exactly 2,1. Two comma 1. Right, so we have exactly the 2,1. And so then what exactly do we do here? So this is 5 multiplied by 2, 1 plus the actual resistance, internal resistance. Then what is the internal resistance here? We realize at this point that the internal resistance is unknown. We don't know what the internal resistance is here. Simultaneously, we can be in a position to then say, so when S1 and S2 are closed, when S1 and S2 are closed, because now switch S is now opened. Switch S1 is now opened, while S2 remains closed. And the reading on the... Now, remember, we have this story here. We have this particular story. Let us continue and see what we have here, as a matter of fact. Let us see what we have here, as a matter of fact. Okay. So now, at this point, you then say, if then we know that the reading on the ammeter A2 is now this, when S2 remains closed and S1, this switch here is opened. So if S1 is now opened, it means no current is going to be passing through this here. So, and the reading on ammeter A2, this one is going to be 3,64 multiplied by the resistance of the external circuit, 3 plus R, like this. Three plus R like that. So, which means that what we have here are these two formulas. So which means that we have that EMF must be equal to EMF 5 times 2.1 plus R 3,64 3 plus R. So let us actually determine and compute this here and see what we can do here. So now let's use our calculator to compute this. Let's use our calculator to compute exactly what we're getting here. Right, a couple of things therefore remain important. 5 times 2.1. 5 times 2.1 is 10.5. 10.5. Which is 3.64. Which is 10.92. 10.92, the 3.64 times 3 is 10.92. 10.92 plus the 3.64R. Let us continue here with this and say what then are we going to have? Then we have the 5R minus 3.64. 5R minus 3.64. Right, so you have 5 minus 3.64. One point 36. 1.36. 1.36, which equals 10.92 minus 10.5. Okay, so that's what we're going to do. 10.92, I'm sure you can guess that one, minus 10.5. 0.42. $1.36. Divided by 1.36. 0.31. 0.31 ohms. 0.31 ohms. That is the internal resistance. And therefore, it means the EMF is I, R plus internal resistance. And we know that the total resistance, or rather the total current, is the 3.5 and the 1.5, which is 5. The external circuit would therefore have 2.1 and then 0.31. And therefore, what is this? What exactly is this here? What is this exactly? So what you're going to do, it is 5 times 2.1 times, or rather plus 2.1 plus, this one is 0.31. Okay, I'll check your message. I'll check your text, your chat. 12.05. Okay, I'll check your chat. So what we're then getting is therefore that the EMF is 12.05 volts. 12.05 volts. Okay, good. Don't only consider, well done, that's interesting. Don't you only consider the circuit with the closed switch for the EMF? Well, we consider both cases, both open and closed. Both open and closed. Like here we said for S1 and S2 closed, we got the 5. Open bracket 2.1 R. But when S1 is opened, 3.64. And then you equate these things and then you're able to get the answer. You're able to get the answer. You're able to get the answer. Okay. Okay, that's a good question. With the open switch, the reading, if the switch S1 is open, then these ones are like out. These two resistors are out, and then we shall only be looking at the 3-ohm resistor together with what? We shall be looking at the 3-ohm resistor together with everything else. This and the battery and the ammeter A2, because with the switch S1 opened, this is like out. The 2-ohm resistor, the 5-ohm resistor, and the A1, they're like out. So we're left with 3 ohms and the 5 volts and the A2 current resistor. So that is what then we have. That is what we have. Yeah? Okay, that's a good question. Why did you use those resistors then? Okay, we considered to calculate the EMF. Okay, you see, why did you use those resistors? Because to calculate the EMF, we could have used the fact that S1 is opened. If S1 is opened, then it means there's no current passing through because electrons do not jump. So would say there's no current passing through, then we're gonna use, if S1 is open, then A2 reads 3.64 amperes, and now you have only 3 ohms of resistance externally, plus the internal resistance of the battery. You see, with that mentioned, it's not enough because we would have got only this formula here. We would have only got this formula, but this formula alone, it's not enough. Why? Because we have 2 unknowns. We still have E for the EMF and also R. So we could just do nothing with this, but we needed another formula. And so we realized that we must also consider when S1, S2 is closed, because there's other information we have there. There's other information that we have, and then we can solve these 2 equations simultaneously. Because now we have 2 unknowns, E and R, and then we need 2 equations. Because with this one alone, if we use the 3.64, the EMF and the resistance, then the question is, how do we find EMF here? Because the internal resistance is not given. But using these 2 equations, we equated the EMF, and then we're able to get the internal resistance, which was 0.31. If the internal resistance were given, then we would have used it. But it was not given. So in other words, we actually determined the EMF, and then we're able to equate the E to the E, and then we got the internal resistance 0.31. After we got the internal resistance, then we substituted as 0.31, and we're able to get the answer, meaning our EMF itself is equal to what? Is equal to 12.05 volts, which is what we wrote here. Any question? Yeah, it is our hope that that is a bit clear, and we move on to the next one. Okay, yeah, let me see. They were saying that. Okay, let me explain again. Right, the explanation is as follows. Okay, in 8.3, they said what? They said switch S1 is now opened. And I drew this one. S1 is now opened. If S1 is now opened, it means there's no current passing through these particular components. So there's no current passing through this resistor in that one. So, and also there's no current passing through A1. And so ammeter A1. So in other words, the meaning is therefore that the current is only passing through this one, the 3-ohm resistor and other components up there, but not at the bottom here. So, but they said if the S1 is opened while S2 remains closed, the reading on ammeter A2 is now 3.64. So they are saying the reading on now ammeter A2 is 3.64. What has happened to the reading? Has it increased or has it decreased? Because it was 5 amperes before. It was 5 amperes before, but now it is 3.64. We can see that the reading has what? The reading has decreased. It has decreased from 5 amperes to 3,64 amperes. Why did it decrease? Why? Because switch S1 is opened. If switch S1 is opened, what is happening to the equivalent resistance? So S1 is opened, it means we removed these two resistors, right? And by so doing, the equivalent resistance was 2,1. If we combine the 7 and the 3, 7 ohms for the 2 and the 5 and the 3, we got that the external resistance here was 2,1 ohms. But when we open the switch S1, then the resistance is now 3 ohms, meaning the resistance increased. There was an increase in the resistance, which led to a decrease in the electrical current. So the current, therefore, decreased from 5 to 3,64. So now if we use the formula, EMF equals I, open bracket, R plus R, we'll then say, what is the reading on the ammeter A2? A2 is connected to the battery, so it reads like the total current. And the total current is what? It is 3,64. Okay. Now, so in the I, open bracket, R plus R, the current now is 3,64, which is the total current, 3,64. What is the external resistance? The external resistance is only the 3 ohms, because these ones are like disconnected now, because just opened this switch, no, there's no current passing through this part of the circuit, so it's only 3 ohms. That's why we put 3 ohms there in the place of the big R for the external circuit, and then we have the internal resistance. So after substituting this 3,64, we got only this formula. This formula. But again, you see, the problem with this formula is what? This formula is clear. It is only this. From the 3,64 they've given us, and then the 3 ohm resistor for the external circuit, and then the internal resistance, but also the EMF. Now the question then it remains, what do we do with this? Because we want to find the EMF, but the examiner did not give us the internal resistance. So surely we need the internal resistance to get the EMF. But how do we find the internal resistance? There's no other way. We must go back and close this switch and use the information we had before. So we're going to say EMF is I, open bracket, R plus R, because now we want to get the internal resistance. How do we get it? Because it's not given. And then now we'll then say, what is the current through the circuit? Then we'll say, okay, the current before was 3,5 with the 1,5, which gave us 5 amperes. So the current was 5 amperes. Yep. And then the external resistance was 2,1 amperes. 2,1 amperes. Okay. 2,1 amperes. Plus the internal resistance. What is the internal resistance? Still, we don't know the internal resistance, but at least before we know that when the switch, both switches were closed, S1 and S2 were closed, then we had I was 5 amperes before, the 1,5 and the 3, and then the external circuit had 2,1 ohms. And then now we have these two equations. And then now it's better with these two equations, because we have these two equations in two unknowns, E and the R. So, but if this is one circuit, is the same circuit, then the EMF under any conditions must be the same as the EMF under any other conditions. Because it's the same battery. Because the battery is the same. Because the battery is the same, we expect the EMF to be the same. Therefore, now, we then say E is E, EMF is EMF, so that now we have 5, open bracket, 2.1 plus R, and then the 3,64, and then the 3 plus R. And then we solve everything here, we get that the internal resistance is 0.31 ohms. After having obtained the 0.31 ohms, we have what? It follows then that we got the internal resistance. Then that's all we needed. That's all we needed. So that we come and then use any of these, like can use the top one. The EMF is I, open bracket, R plus R. What is the I? 5. Then, what is their, yeah? Yes, you can also use the bottom one. We can also use the bottom one. The answer is the same. Let us check this. Let us check this. Let us use the bottom one. Right, so if you use the bottom one, for example, you're going to say, oh, all right. Okay, good. Yeah, we can also use the bottom because these are like simultaneous equations. Yes, simultaneous equations. So you can say, for instance, the EMF is the I. What is the I? It's 3,64. And then the bottom one is 3,64. 3 plus 0,31. Okay, so you have the 0,31. Let's use the calculator now. Let us use the calculator. Three plus 0.31, which is exactly 12.04 or 12.05, 12.05, yeah? So you'd get actually exactly 12.05 volts. And the 12.05 is what we got even when you use the top one. And we're also getting 12.05 when we use the bottom equation. So your same thing. Let's look at the next question. Okay, we are back to and still looking at this particular question, and we're saying switch S2 is now opened while S1 is closed. So now we open this one. So now we open this one. So S2 is now opened while S1 is what? Is closed. How does the voltmeter reading change? Choose from increases, decreases, or remains the same. Explain your answer. How does the voltmeter reading change? Okay, good. Let us check. Well done. Very well done. So the correct word must be increases. The correct word must be increases. Why? Explain the answer. The explanation is going to be that total resistance increases. Total resistance increases. Current decreases. Total resistance increases. Current decreases. But also you can go on to then say the V internal, or what we call the internal volts, right? So the internal volts decreases. The internal volts decreases. So now it increases because the total resistance increases. So how does now, when switch S2 is now opened, here switch S2 is now opened, while switch S1 remains closed, how does the voltmeter reading change? Choose from increases, decreases, or remains the same. Explain the answer. Explain the answer. So the total resistance increases because when we open this switch, it means that we remove this 3, because this 3, there's going to be no current passing through the 3 ohm resistor, but there's going to be current passing through these 2 and the 5. Meaning the resistance is going to increase to 7 ohms. It's going to increase to 7 ohms. Okay, so the resistance is going to increase to 7 ohms. So that in the end, if this resistance increases to 7 ohms, then the total resistance is going to increase. Because before, if you have everything, the total resistance was what? In the external circuit was 2.1 ohms, but now it's going to be 7. So the total resistance increases when we open switch S2. The current therefore decreases because R equals V over I. So when the total resistance increases, the current therefore decreases. V internal, or the internal volts, then decrease. Okay, so this is what we have. That will be the explanation for the answer. To explain how does the voltmeter reading change? We're to choose from increases, decreases, or remains the same. Right. We continue. Right, so question 8 must be started on a new page. The second diagram below shows a battery with EMF 12 volts and then an internal resistance of 0.5 ohms connected to 3 resistors, R1, R2, R3, a light bulb. There's a light bulb there. A switch is there, an ammeter, and connecting wires. An ammeter is here. And the wires that are connecting wires. Right, the ammeter and connecting wires have negligible resistance, yeah? So we are sure, therefore, that the ammeter and connecting wires have negligible resistance. State Ohm's law in words. State Ohm's law in words. I know that this one is something that is easy. Let us practice, please, and make sure we remember this all the time. Please, you need to write the laws down. Write the laws down. All the laws. All the laws. All the laws in electricity, you need to write them down. And the definitions. The laws and definitions of electricity, we need to get a summary of those and write all of them down so that you can remember them. Yes, you must include the light bulb because the light bulb is a resistor. When you do the calculations, you need to include the light bulb because the light bulb is what? It's a resistor. Okay, so here we then say the potential. The potential difference. Voltage. The potential difference of voltage across. Right, across a conductor. Is directly proportional to the current. To the current in the conductor. In the conductor at constant temperature. At constant temperature. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. At constant temperature. The potential difference of voltage across a conductor is directly proportional to the current in the conductor at constant temperature. Okay. So, this is what we have. And this is what we call Ohm's law. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. This is one way to state Ohm's law in words. We move on to the next question. Let's do some calculations. The circuit diagram below shows a battery with an EMF of 12 volts. 12 volts and an internal resistance of 0.5 amperes connected to 3 resistors, a light bulb, a switch, an ammeter, and connecting wires. The ammeter and connecting wires have negligible resistance. Switch S is initially closed. Calculate the total external resistance of the circuit. Calculate the total external resistance of the circuit. Okay. Oh, you got 15. Let's check that one. Let's check that one. Yeah, you're on point. So now, to calculate the total external resistance of the circuit, you would then be in a position to then say the total resistance here would be given by the following. So you can just do this series. So 1 over R parallel is 1 over R1, 1 over R2. 1 over R1 for the parallel ones, 1 over 10, 1 over 10. This is 2 out of 10. R parallel. Okay, 2 out of 10 is 1 out of 5. Then the R parallel, then you reciprocate, take the reciprocal, which is 5 out of 1 ohms. And therefore, what then we're able to get here is that R total, right, which is what is R total? Okay, so you add everything, yeah? So it's going to be 5 ohms for this one, for the parallel combination. And then when the switch, S is initially closed, right? So if the switch S is initially closed, as it is closed, you need to find the total resistance there. And then you have the RL, which is actually exactly 10. This is 15 ohms. Right. So okay. So that would give you the total series. That will give you the total series. Okay, that will give you the total series. Okay, right, that will give you the total series. Right, when it gives you the total series, then it gives you this here. But now you'd have to combine with this because it's going to be parallel with this. So which means that the resistance we want is going to be some parallel resistance. Right, and then now we can just use a shortcut. And then we have, you can call these, so you will have R3 multiplied by the one that's going to come out of this, yeah? Total series, you divide by the R3 plus R total series. So which means that R parallel. What is R3? And then you have the 15. What is 15 by 15? divided by 30. Right, so let's use a calculator here. Okay, so 15 by 15 divided by 15 plus 15, which is 7.5. 7.5. So which is 7.5 or 7.5 ohms. And that is going to be what exactly is required. But first, we need to do the total series. But first, we dealt with the parallel, 1 over R1, 1 over R2, 1 over 10, 1 over 10, 1 over 5. Okay, so you have the 5 ohms. Then with the 5 ohms, then you would add everything. So you have the 5 ohms for this, and then you add to the 10, which is 15 ohms. And then you have 15 by 15, 15 plus 15. Yeah, so the answer that they want, yes. Okay, you're saying why are we including the 15 ohm resistor? Because the switch S is closed. Okay. Yes, because the switch S is closed, that is the reason why we are also including the 15 ohm resistor, because the switch S is closed. That is why now we are actually involving the R3, because the switch S is closed. Because if the switch S were open, if it were open, then this one was going to be out. No current was going to be passing through it, so we're not going to include it, yeah? Okay. Oh, okay. All right, that's fine. Okay, we move on to the next question. So the question is, what is the answer to the 8.2.1? The answer, you can say, the R total external resistance is 7.5. Which is 7.5, yeah? Which is 7.5. Seven comma five. Yeah, it's 7.5 there. 7.5. So we continue. We continue. We continue. Right. Right. We continue. Next question. Next question. Now we want to do 8.2.2. The reading on the ammeter. Switch S is initially closed. Switch S is initially closed. Reading on the ammeter. Let me give you a minute to do this one. Want to find the reading on the ammeter. There is the ammeter. What is the reading on the ammeter? Yeah? What is the reading on the ammeter? What is the reading on the ammeter? So we continue. Okay, let me see what you've done. Okay, you're saying it's 1.6. We're going to check that. 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 Okay, now we want the reading on the thing, on the ammeter. Okay, let us do the reading on the ammeter. The ammeter is sitting there. EMF is IR plus R. Right, and we actually want to find, so we can use the following. What is the EMF of the EMF is 12 volts with an EMF, the battery has an EMF of 12 volts, so you're going to put 12. We have the current we want. The resistance, we got 7.5 plus the internal resistance 0.5, 0.5 ohms, which is 12, 7.5 I plus, okay, let us add these things here first. Because we have 7.5 plus 0.5. What is 7.5 plus 0.5? It's exactly 8. So it's going to give us exactly 8I. So you divide. You have the 12 equals 8I. Divide by 8. Divide by 8. 4 goes how many times? It goes 3 times, 2 times. 1.5 amperes. 1.5 amperes. 1.5 amperes. Okay, so yeah, that's the answer we gave. Okay, because I used that. Let me just see. Okay. Okay, yeah, but why is it? I'm wondering. I'm trying to check with the calculator because I just did it off the top of my head. Oh, okay. You did not add the internal resistance. That's why you did not add the internal resistance. So obviously, for the EMF, we must use this formula, and therefore we must add both the external and the internal resistance. Okay, I was trying to see why your answer was different. Okay, but now I can see that obviously you said 12 divided by 7.5, so you left out the 0.5. But now always for EMF, we must use this formula. So now that is something that is very important. Okay, let me see. Yes. Okay, yeah, why must you add Why must you add the R? Because EMF includes both external and the internal. I hear you there. Because EMF, okay, now we did the 7.5 plus the 0.5, which gave us 8. And then went on to then say 12 divided by 8. 1.5. 1.5 amps. Okay, 1.5 amps. Okay. Yeah, that's the thing, because I can see that you said you used the formula. You used the formula R equals V over I, and then you wanted to find the I, so you said I is V over R. And then this formula is okay, but this formula only works here. It doesn't deal with EMF, this one. It only works on the component of the circuit. When the current is passing through a conductor, then you can use this one. But pertaining the battery and the EMF, because we want to find the reading on the ammeter. So, okay. Okay, yeah, there's something that is, let me see. Yeah, when there's EMF, you can't, because, I mean, you can still do, but now, what did you do? Okay, you see, you said 12 divided by 7.5, and this 12 is the EMF. And the 7.5, I agree, it's the R total, which is 7.5. Okay, let me see. Oh, all right. Yeah, that's the thing, because I can see you used the 12, but the 12 is EMF, and it must include internal and the external. So it must use both, it must include both 7.5 and 0.5. Okay, it's something you need to check there. Okay, so but that was the reading on the ammeter. All right. Okay, good now. We'll move on. So that was the reading on the ammeter there. So the reading on the ammeter is actually exactly I equals 1.5 amperes. 1.5 amperes. Now we need the power. The power. What is the power dissipated by resistor R3? Power dissipated by resistor R3. What is it? Okay, so power dissipated by resistor R3. This one, I'm giving you like 2 minutes to do the power dissipated by resistor R3. 2 minutes. When you're done, please let us know. Right, right. Please let me know when you're done. Just let us know when you're done. Then we're gonna just do it. Because for 4 marks, we want the power dissipated by resistor R3. What is the power dissipated by resistor R3? Please let us know when you're done. power dissipated by resistor R3. Okay, let's see what you've got there. Right, you think it is 8.44 watts. 8.44 watts. Well done. I must indicate that up front. Well done. So now, the couple of things that we're going to use. Power. I squared R. So, but a couple of things that we know. We know that V is IR. Because R3 will provide us with 15 ohms. So now check. Okay, now let us reason together. So the question then is, what is the potential difference here? What exactly becomes the potential difference there? Because you already know that it is resistor R3, so, but we're interested in also knowing what the current is that passes exactly through that part. So obviously the couple of things that we can use here. Right, so if you use V equals IR, we have already found the potential difference across this here. Right. Or alternatively, the easiest is to then say, believe that this is the easiest one. The actual current IR3 which is R parallel. Okay. So what you then can do to get the current through the R3 is to actually deal with the R parallel against the R3 times I total. Okay, this is easier because you just want to find the current through the R3. So there are many ways to do it, but this is surely one way to do this. So that in the end, what then you are able to get here becomes exactly that. You have 7,5 with the 15 multiplied by 1,5. And if you use a calculator, yes, there are many ways. There are many ways to do it. There are most certainly very, very many ways to do it. Yeah, you see, I know that there are many ways to do that. You can actually use all sorts of ways, but this would be one of the methods we can use. So it will then be, in particular, we'll explore some of the methods here. So meaning that you'll have the 7.5. Okay. 0.75. 0.75. 0.75. You square this. Okay, so this is going to be 0.75, and then it is R3 with 15. Right, and therefore use the computer here to get the answer. But yeah, I said there are many ways to do it. There are too many ways to do it. I was just thinking of which method. So you have this one squared multiplied by 15, which is 8.44. 8.44 watts. Okay, so this is then what we can do. So now this would be the power dissipated, and obviously, well done, you got the same answer. But as indicated that there are too many ways to do this particular question, because you have already got the reading, ammeter reading, which is 1.5, which is exactly 1.5, right? So if it is actually exactly 1.5, then that is what we used here. So we took the 1.5, and this 1.5 can be used. So you can use ratios, and then say the 7.5 ohms are parallel. You divide that by the R3, and then you are able to actually get the correct answer here that is required, which is 0.75. So I, which is 0.75, you square times 15, and therefore it is 8.44 watts. 8.44 watts. Okay, so that is something that you need to look at and think about so immensely. Think about so much immensely. But once again, there are too many ways to do this particular calculation here. So this is one of the ways we certainly can be in a position to use here. And we move forward. We actually obviously move forward to the next question. Move forward to the next question. Okay, at this point, switch S is now opened. So now switch S is opened, and yes, it is closed in the picture, but it is now opened. If the resistance of the light bulb remains constant, if the resistance of the light bulb remains constant, how will the brightness of the light bulb be affected? Choose from increases, decreases, or remains the same. Explain the answer to question 8.3.1. Okay, we shall do that. So Switch S is now opened. If the resistance of the light bulb remains constant, how will the brightness of the light bulb be affected? Choose from increases, decreases, or remains the same. Right. I'm giving you this one 1 minute. Then we shall discuss it together. I'm giving you this one a minute. I'm giving you a minute. All right. We continue. Please try that one. Please try that one. Please let us know when you're done. Please let us know when you're done. Right. 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 We continue. Yeah, please let us know when you're done. Okay. The resistance of the light bulb remains constant. How will the brightness of the light bulb be affected? Choose from increases, decreases, or remain the same if the switch S is opened. Mm-hmm. Right. Right. So we continue. Okay, let us know when you're done, please. Let us know when you're done. Right. How far now? How far now? How far now? So now we have the following. Right. Right. So we continue. We continue. How far now? I'm sure you're still thinking about it. Oh, you sent it long back. Okay, that's fine. Okay, I can see increase or remain the same. Remains the same. Remains the same. Okay, that's fine. I just needed an attempt and then we shall discuss together what actually the answer is to this question. So, and here is the answer to the question. And this is actually the answer we're going to accept in this particular question, but obviously it was given exactly 1 mark. Right, so given only 1 mark suggests that obviously in 8.3.1 you need to write a lot. So obviously we agree that it increases. We agree that it increases. So the fact that now the switch S is now opened, it means that R3 is removed. When R3 is removed, some of the current was passing through R3. So which means that the current that is passing through R3 is not going to branch anymore. A lot of the current will be going through the light bulb. So we expect that more current will be passing through, and therefore we expect the brightness to increase. And there are several reasons for this. So this is 8.3.1. So we expect that it increases because the current is no longer will no longer be going through many things. But okay, okay, okay. It says that the light bulb, the resistance of the light bulb remains constant. Why? Because they want us to be in a position to use Ohm's law here. Because if in other words, the resistance of the light bulb remains 10 ohms, Because why is that necessary? Because the problem is that Ohm's law works at constant temperature. But we know that the examiner was trying to make sure that there's no ambiguity here, because another student can come and say, this light bulb is hot, meaning that this is not going to obey Ohm's law. But so for the examiner to cover their back and make sure the question does not become ambiguous is to say the resistance remains constant. Because now somebody can say the temperature is not constant because it's hot. And therefore, this is not going to obey Ohm's law. And therefore, its resistance is going to change because of the heat, of the temperature. That is not. That is actually increasing, suppose, or because of the heat, the temperature will affect the resistance. Another student can make that kind of an argument. That is the point. Yes, the heat comes from the light bulb. Because most of these conductors in the light bulbs are not purely ohmic conductors. They're not ohmic. Okay, because of this, the examiner had to make sure that the resistance is constant, because somebody can say there is heat. The temperature is not constant. So how do you then say the resistance is constant? So the examiner can say, okay, we're interested in the resistance here. Let's just say the resistance of the light bulb remains constant because it's getting hot. This light bulb is getting hot. It's glowing. The only way is to make sure that the resistance of the light bulb is constant. Then we can do everything else. Okay, because if ever then the resistance change, if the temperature, obviously there's heat, the light bulb is glowing. Its temperature is not purely constant. We can say that. So, I mean, in reality, we can't imagine the temperatures being constant quite at least over a period of time. We expect the temperature of the light bulb to be such that it increases over time, etc., etc. But when you switch on the light bulb, it's initially cold, and then it warms up, it warms up, it warms up. So the examiner has to then say, okay, the resistance remains constant. If the resistance remains constant, then we can do everything else, and then we can expect to use notions of Ohm's law. And the reason, therefore, is, I mean, some of the current was going through that, some of the current was going through that. At this point, the current is going to pass through that. It's not going to branch through the R3. Okay. So that is something that is very, very important here. So we expect, therefore, in 8.3.1 that the resistance, rather the brightness, because they're saying, how will the brightness of the light bulb be affected? So yeah, we expect the brightness to increase. Why? First point, we need to explain the answer here in 8.3.2. The total resistance of the circuit increases and the total current in circuit decreases. Power output increases. Okay, therefore, brightness increases. The V internal, The internal, or what you call the internal volts, or the lost volts, V loss. V loss decreases. V loss decreases. And V external, which are the external volts, increases. Increases. Okay, now let us discuss these together and see what then is the explanation for the light bulb to actually have its brightness increasing. So the total resistance of the circuit increases. Right, so we note that the total resistance of the circuit increases and the total current in the circuit decreases. Right, so the power output increases. Therefore, the brightness increases. So we're effectively then saying the power output is what is associated with what? With brightness. It's what is associated with brightness. Because this one is 15 ohms. But when you open this switch, it is cut out. And then here you have this one is 5. We did this one. 1 over 10, 1 over 10, 2 out of 10, and then it is 1 over 5. Okay. So, which is 5. 5 plus 10, 15 ohms. Okay, so here you're going to have like 15 ohms. Yeah? Right. So, if you have 15 ohms here, what then is this? Okay, you'll have 15 ohms, and with the 15 ohms, it means therefore the total used to be 7.5 ohms, but now it's going to be 15. See, the 7.5, it's when we combine these things. We did it before. It's when we combine these things, we got 7.5. But now here, it's 15. 10 plus 5, 15. So the total resistance of the circuit increases, and the total current in the circuit decreases. Total current decreases by inverse proportion. The power output increases. Therefore, brightness increases. The power output increases. Right. And the brightness increases, or the V internal, the internal volts, or the lost volts decreases, and the external volts increase. So now you're able to see that the external volts increase. So when the external volts increase, therefore, it leads to an increase in the power, and therefore an increase in the brightness. An increase in the brightness of the light bulb. Okay, think about this. Think about this. Think about this. Okay, think about it. Right. Right. So this is exactly what we're able to observe. This is what we're able to observe. And that will be the reason for the brightness of the light bulb to therefore increase. Okay, in the next question, next subsequent question, you need to be in a position to state Ohm's law. So in 8.1, you must be in a position to state Ohm's law. Okay, next question. Switch S is closed. The reading on ammeter is 3.5 amperes. Calculate the external resistance of the circuit. The diagram below shows 4 resistors connected to a battery of EMF E and internal resistance R. The resistance is of the ammeter. Okay, let us first look at Ohm's law here. I know that we are beyond the time. Do you have something to do now? Do you have something to do now? Please advise, because again, I know that we are beyond the time. Okay, that's fine. Maybe we can just continue and do some of these questions and see, because there are many questions I have prepared. Okay, that's fine. Okay, good. Right, so let's look at question 8 now. This question 8 is the second diagram below shows 4 resistors connected to a battery of EMF E. And the internal resistance R, the resistances of the ammeter and the connecting wires are negligible, while the voltmeters have high resistances. State Ohm's law in words. State Ohm's law in words. Okay, for purposes of learning, I prefer to state the law all the time so that we can remember the law and we cannot forget it. And here is the statement of the law. And I know that we know the law very well, but we start by saying the potential difference. Right, so the potential difference across a conductor is directly proportional. Is directly proportional to the current in the conductor. Current in the conductor at constant temperature. Okay, so the temperature must be constant. That is why that a question to say the resistance of that bulb remains constant in the conductor at constant temperature. And this is true in brackets. We say provided. I know that we stated this in many different ways today. Provided temperature and all other physical conditions are constant. So, okay, this is what we have. Okay, now at this point, this is what we have. This is Ohm's law. We repeat the statement to make sure we can remember it. And we say the potential difference across a conductor is directly proportional to the current in the conductor. Watch the words potential difference across a conductor, because this voltmeter measures the potential difference across a conductor. This potential difference across a conductor is directly proportional to the current in the conductor at constant temperature, provided temperature and all other physical conditions are constant. Provided temperature and all other physical conditions remain constant. Yep. So we note this, we need to remember it. I know it's a law and it's Ohm's law, and obviously it's like something you need to remember as a song. We repeat once more the statement. The potential difference across a conductor, V, is directly proportional to the current in the conductor. So this is in the conductor, this is across a conductor. Potential difference is across a conductor, whereas the current is in the conductor. But these things happen at constant temperature. When the temperature is constant, we have the understanding that even the resistance is constant. Then Ohm's law is going to work. Because if ever there's a light bulb that is getting hot, because surely the temperature of a light bulb increases from the time that you switch it on and the current begins flowing. It's cold normally. Maybe it's winter, for example. Maybe it's winter, and in winter it is cold, and the light bulb is cold. The minute you switch it on, it gets hotter and hotter and hotter and hotter. So its temperature increases. But Ohm's law says, hang on, please. Potential difference is directly proportional to the current at constant temperature. So that is why the examiner in that previous question had to make sure that really our resistance is constant for us to do everything. Okay, we move on to the next question. The second diagram below shows 4 resistors connected to a battery of EMF E and internal resistance R. Okay, good. Let us discuss why the resistance is constant as stated in the previous question. Why was it necessary for the examiner to say the resistance is constant? Would the examiner have not just ignored that part and said, okay, we don't care if the resistance is constant or not. Why was it necessary? It was necessary because there is a light bulb, but because in Ohm's law, we know that as part of the law, there must be constant temperature. There must be constant temperature. But what about if there's a light bulb and this light bulb is getting hot? If this light bulb is getting hot, a light bulb is a resistor. It has very high resistance. That is why it glows when the current passes through. But we're then saying the potential difference across a conductor is directly proportional to the current in the conductor. This potential difference across a conductor is directly proportional to the current in. Potential difference across a conductor is directly proportional to the current in the conductor. But these things are directly proportional at constant temperature. What about if things are getting hot in the circuit? What can get hot in the circuit? What about if the temperature is not constant? How? Okay, if there's a light bulb whose temperature is increasing, from the moment you switch it on, perhaps it can be constant at some point, but from the moment you switch it on, the light bulb is cold and then it becomes hot. It becomes hot or warmer at least. But because of that, then Ohm's law says, please, guys, do not mention the things whose temperatures are changing here. V is directly proportional to I at constant temperature. When the temperature is constant, it therefore would mean that even the resistance itself would have to mention the resistance is constant. Would have to mention because the resistance when the temperature changes is likely to potentially be affected. When the temperature changes, it's likely to be affected because of the vibration of the particles of the material. But yeah, in the end, then the examiner, it was necessary for the examiner to then say, okay, please, something must be constant here. The physical quantities, the physical conditions, provided temperature and all. You see, provided temperature and all other physical conditions are constant, then V is directly proportional to I. But if temperature is not constant, Ohm's law is not true. It doesn't hold. V is not directly proportional to I. This V is directly proportional to I under ideal conditions where temperature is constant. And hence when resistance is constant. Because in Ohm's law, you know that V equals IR. What is this R? R is the proportionality constant. So R is a constant. And therefore, if R is a constant, then it must be constant. Because if ever R is not constant, then we do not have the law. But when is R constant? Well, when temperature is constant. When temperature is constant, then even the resistance is constant. And then we can do our things using Ohm's law. We can use V equals IR because this formula V equals IR does not hold when the temperature changes. When the temperature is not constant, does not hold. So in the case of the light bulbs, for example, it's a different story because the light bulbs do not quite obey Ohm's law as the resistors, which under ideal conditions, we just assume that their temperature is constant. But we know very well that normally when electricity begins flowing through things, things become hot, you know. So because the components become hot in the house when the electricity flows, the things become hot, whatever it is. The iron becomes hot, the things become hot. The question then is, when does Ohm's law really hold? Because the temperature is not constant most of the time when electricity actually obviously begins flowing through substances. So these are the kinds of things that are important. Okay, we move on. The second diagram below shows 4 resistors connected to a battery of EMF E and internal resistance R. The resistances of the ammeter and the connecting wires are negligible. While the voltmeters have very high resistances. Okay. While the voltmeters have very high resistances, these are not just ordinary voltmeters. These voltmeters are like resistors. There's a voltmeter V2, there's a voltmeter V1, but they are like resistors. This is like we have put another resistor here. It's like we have put another resistor there. These are not just your ordinary voltmeters. But let us answer the questions. Switch S is closed. Okay, so there is a switch S. This switch S is closed. The reading on the ammeter is 3.5 amperes. 3.5 amperes we can see. Calculate the total external resistance of the circuit. Calculate the total external resistance of the circuit. Okay, please, I'm giving you some 2 minutes. I know it's easy. Some 2 minutes. Let's try this one and see some 2 minutes. How do we then find the reading on the ammeter? Okay, let me know when you're done, please. Then we shall discuss. Okay, let's see what you've got. 4.83. Very well done. Very well done. So now at this point, we're going to just do this cautiously. And to do this, we're going to actually consider the parallel ones. So we're going to have 1 over R parallel, which is 1 over R1, 1 over R2. 1 over R parallel is 1 over. The R1 is 1. R2 is 5. Okay. So now, what is this? What is 1 plus this? So 1 over R parallel would be, you put the 5 here, then you have 6. And this means that the R parallel is going to be, you invert, take the reciprocal of this, which is 5 out of 6. Five divided by 6, which is 0.83. So 0.83, which means that we have R total 0.83 plus. Okay, so this is for the parallel ones. Remember, the parallel, these ones are like in series, the 3 and the 2. Anyway, you got that right. So, okay, so now you're going to add the 4. Our total is 4.83. 4.83 ohms. 4.83 ohms. All right, so yeah, this is 4.83 ohms. Okay, so this is the answer, and you got the same answer, so good. Okay, but we are moving to the next question. And then now, that was our total, which is 4.83 ohms. Calculate the reading on voltmeter V1. This one. The reading on voltmeter V1. Yeah, I'm giving you a minute. Okay, very well done. 16.91. So obviously at this point, we're going to use our old friend Ohm's law, because we assume the temperature is constant and the things are not getting hot. So that we have R equals V over I. And at this point, this is Ohm's law. So this means that you have 4.83. 4.83 is the total resistance outside the circuit, external circuit. V over the current. The current is 3.5 amperes. By dint of cross multiplication in algebra, we get 4.83 in parentheses by 3.5. Therefore, 4.83 by 3.5. Let's do this one. Okay. So which is 4.83 times 3.5. Which is 16.91. 16.91. 16.91 volts. 16.91 volts. .91 volts. Okay, so this is the answer you got also. This is the answer you got also. 16.91, but you can also take 16.92, something like that. But we got 16.91, right? We got 16.91. Just check. Yeah, 16.91 volts. Now, next, we're going to deal with the next question and focus on what we have here. So we're going to look at 8.2.3. Okay, this was 8.2.2. We found the voltmeter reading voltmeter 1. How does the reading on voltmeter V2 compare to the reading on voltmeter V1? Choose from smaller than, equal to, or greater than. How does the reading on voltmeter V2, this one, compare to the reading on voltmeter V1? How does V2 compare to V1? Choose from smaller than, equal to, or greater than. Okay, let's see what Noah is going to say there. Good, very well done. So in other words, it is smaller than, right? Yes, it is smaller than. It is smaller than. It is smaller than, yeah? So why would this be the case that this is smaller than? Why would it be the case that this is smaller than? Right. Why would it be the case that this is smaller than? Okay, obviously there are several reasons for this. There are several reasons for this. Okay. Good. Most definitely. So it's about the fact that you're able to see that the V external decreases. Good. So you're able to see that the V external decreases. Right. So you're able to see that the V external obviously appears to most certainly decrease there. So obviously you're seeing that in this case, the reading on voltmeter V2 here is actually smaller than the reading in V1 or on the voltmeter V1. The reading on voltmeter V2 is actually smaller than the reading on the voltmeter V1. Right, it is actually smaller than. And you see, there are a couple of ways to look at that as we pause to think about this. Because if you check very carefully, V2, V1, what is V1? So this V1 sort of measures the EMF. V1, voltmeter 1, measures the EMF of the battery. But V2 has to do with measuring the potential difference of those resistors with which it is parallel. And now you have extra components like 4 ohms. And as a consequence, it is clear, therefore, that V1 would have the greatest measurement because it measures the EMF. And these ones are like the external circuit whose summation must produce V1. Okay. Right. So at this point, we're looking at the fact that V1 is a voltmeter connected across the battery. So if you connect a voltmeter across the battery, it measures the EMF of the battery. Okay, so how do we measure the EMF of the battery? We put a voltmeter across the battery. Then that is going to measure the EMF of the battery. And the EMF is the maximum amount of energy that the battery can produce. Maximum amount of energy that the battery can produce. At this point, the battery, if you put a voltmeter, is going to give us the maximum, the greatest potential difference. Yeah, so V1 is EMF, and it is the biggest one. But this V2 is measuring the potential difference across these particular two components. Yeah, it's measuring the potential difference across these particular two components, 3 ohms and 2 ohms. So V2 is external. Yes, so V2 is external. That is why V2 is smaller than V1, because V1 is everything, is closer to the source, is measuring the EMF of the battery. The EMF is the biggest power potential difference you can get. It's the biggest energy we can get from the battery. It's the maximum amount of energy that the battery can produce, electromotive force of the battery. And this one is external, and this external is small. It's smaller because it's a potential difference here. But if you add the potential difference here and the potential difference there, you will then be able to get the EMF. Or even then, it is external, so it's still a little bit less. Because this is V external. So this V external is going to be smaller anyway. It's just going to be smaller because this one is the EMF. So the EMF is the biggest. Because if you look at the EMF formula, the EMF, we said it is R plus that. So now it is IR. Okay, this is the EMF formula. I into R plus R. So in other words, now this one is going to be V external with the V of the lost volts, V internal. So now EMF now is, this is V external. So V external plus V internal would give us EMF. In the end, we can see that indeed the EMF is bigger because this one is the EMF. So it's bigger than the things that are like external. You know, that is why here we then say the V2 is smaller, it's external, and the EMF is everything, it's powerful, full of power. It is the total, it is rather the maximum amount of energy the battery can produce. Yeah, so I'm sure it is clear there. We'll move on to the next question. Okay, now we're going to look at like 8.3. Okay, the story above is still the same, and we're still looking at the same circuit. Elena concludes, okay, there's a conclusion. Elena concludes that the EMF of the battery is equal to the reading on the voltmeter, on voltmeter V1. Okay. Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. Okay, define the term EMF. Let us first define the term EMF. EMF means maximum work done. Maximum work done by the battery. per unit charge. Okay, this is maximum work done by the battery per unit charge. The total. The total amount of electric energy supplied by the battery per coulomb. Or per unit charge. Okay. So that is the definition of EMF. Maximum work done by the battery per unit charge. Right. So just take note of that. Right. Right. So that is what we have. That is what we have. But now also the EMF is the maximum work done by the battery per unit charge. As much as obviously you know that EMF is what we call the electromotive. Electromotive force. Electromotive force. Yeah, electromotive. That's what we're saying. Electromotive. Electromotive force, yeah? That's EMF. E for electro, M for motive, F for force. But by definition, it is the maximum work done by the battery per unit charge, or the total amount of electric energy supplied by the battery per coulomb. Okay, I want us to analyze the next question very carefully. Is the learner's conclusion correct? Yes or no? Is the learner's conclusion correct? Yes or no? Okay. This one, obviously, we need to look at it very, very carefully. There are several reasons that we will then allow, and there are several conditions under which we can say the voltmeter will measure EMF or not. But because this battery has internal resistance, if the battery has internal resistance, some of the volts will be lost inside the battery. Okay, so we must be careful here. If the battery has internal resistance, not everything is going to come out. Not all the EMF is going to come out. So not all the potential difference will come out because some of it is going to be lost. So in view of the lost volts, would say in the presence of internal resistance in the battery, because it's not negligible, the internal resistance is not negligible, would say it is close to measuring the EMF, but it's not an accurate measurement because of the lost volts in the battery. So if the learner now is to be very careful with the terminology they are using, in terms of if the learner concludes that the EMF of the battery is equal to the reading on voltmeter V1, because the learner can be like, okay, how accurate is V1 in terms of it measuring exactly the EMF? Okay, good, good. So now, in other words, it measures the greatest EMF you can get, the greatest potential difference you can get. But if the R is zero, if the R is zero, then it will measure the accurate EMF. I get what you're saying. But obviously the V1 would measure the EMF when the internal resistance is zero. Strictly speaking. Okay, now we are being very strict in terms of language. If the internal resistance of the battery is zero, we then say V1 measures the EMF. What about if the internal resistance is not zero? So, in other words, if you look at EMF, is I, which is R plus R. If R is zero, which is ideal, which is an ideal condition. But I mean, this would measure the greatest possible potential difference you can get. But once again, in the presence of the potential difference, in the presence of what? Of the R. So the learner is supposed to be careful here and look at whether R is zero or not. Because if ever the internal resistance is zero, yes, EMF is going to be equal to V, it's going to be equal to the V1. It's going to be equal to the V1 or the V external. Okay, I want us to be very careful in terms of language here. So, strictly speaking, we want to say that the learner obviously will be tempted to think that this would be actually exactly equal to EMF, but you need to tell the learner something more and say only when the internal resistance is zero. If the internal resistance is not zero, then some of the volts are lost inside before the terminals are reached. Before we reach the terminals. Before everything goes through the voltmeter. Okay, obviously, well, that is why the examiner said you need to give reasons, because it's a very contentious issue, but it is because of the lost volts. And this is what the explanation we're going to give the examiner. In 8.3.3, it is nothing more than the internal resistance, the battery. One mark, you don't need to write a lot of things. The battery has internal resistance. So it won't be the accurate EMF. Okay, because I know it's tempting to think it is, but it is exactly, this V1 is exactly the EMF if the internal resistance is zero. But this battery has internal resistance, and therefore a little bit, there will be some lost volts, very small, but they'll be lost. Very small, but they'll be lost. Okay, so that is something that you need to take note of. This is very small, but lost volts will happen in the presence of internal resistance there. Okay, so, but as said, if R is zero, then you can be rest assured that V1 is EMF. But if R is not zero, then it means that V1 is not EMF, because it means that EMF is bigger. Okay, I'm glad that this question came, because the examiner realized that it's a small little thing we need to make as a comment for the learners to understand this. So, because when would V1 be EMF? V1 is EMF, strictly speaking, when the internal resistance is zero. But if the internal resistance is not 0, then they are lost volts. They are lost volts inside the battery. Okay, meaning we would have less potential difference that's going to come out. Or alternatively, we can say EMF is V external plus V internal. This means that the EMF is bigger than the V external. I mean, that's another way. So the EMF is bigger than the V external because of the lost volts. That's the reason. Just the lost volts make the small difference there in the reading between the EMF and what the voltmeter is going to read. Okay, let's move on. So this was 8.3.3, just to provide a reason why there's going to be a small difference between the actual EMF and V1 reading. Because of the internal resistance, the battery's internal resistance, that's what makes the difference. If there's internal resistance, then there are lost volts. Lost volts. As much as it measures a high potential difference, but they are lost volts. Okay. Okay, let's move on. Okay. Okay, let's look at 8.4.1. Okay, now in 8.4.1, we're effectively then saying switch S is now removed. Okay. So now they decided to remove switch S. So yeah, there's no switch anymore. And the switch S was where? It was here just above. It was there above the 1 ohm resistor, but now it has been removed and replaced by voltmeter V2. V2 has been put here. So yeah, but V2 was here before, but now it has been put there. V2 has been put there. As shown in the second diagram. This is a very strange thing. Very, very strange thing. Why? Because the voltmeter is connected like this. But the examiner has put it like an ammeter. What is this? Okay, but switch S is now removed and replaced by voltmeter V2 as shown in the second diagram below. How will each of the following change? Choose from increases, decreases, or remains the same. The power dissipated by the 4 ohm resistor. Check this out. Okay, the power dissipated by the 4 ohm resistor. P, power dissipated by the 4 ohm resistor. Okay, yeah. How will the power dissipated? Think about it. Think about it. The power dissipated by the 4 ohm resistor, how is it going to change? Okay, let's see what Noah is thinking there. That's fine. You think increase. Okay, that's okay. You think increase. Remember that this one is like a resistor, because they said that this potential difference, these voltmeters have very high. V2 has very high resistance. Very high resistance, yeah. Okay, let's see. Okay. Okay, that's interesting that you're thinking because we are still like analyzing. Okay, it's interesting that you're saying the resistance will increase because what we know is that these voltmeters are very high. So V2, V1 and V2, just to mention, but yeah, we are V1 and V2 have very high resistance. So the truth is they are voltmeters, but I would say it makes sense for the examiner to connect it like this because I'm like, a voltmeter is put like this, but why is the examiner connected it like that? Okay, it would make sense because very high resistance, because these are like resistors. These two voltmeters are very high resistance. This was the information that they gave us. They said that the resistances of the ammeter and the connecting wires are negligible. The resistances of the ammeter and the connecting wires are negligible, while the voltmeters have very high resistances. The voltmeters have very high resistances. So these voltmeters are like resistors. So this is like a resistor. Okay, it's very interesting that for Neo to think that then the resistance is going to increase. Let us analyze that together. Okay, good. That's interesting that the 1 ohm resistor doesn't work. So this 1 ohm resistor is reasonably small. Yeah, it makes a bit of sense. You can imagine it as being small. That this one is another resistor that is like in series now with this with the 1 ohm, but its resistance is so big, quite big, quite big. Okay, what is going to happen here? So if you imagine this as a resistor, another resistor, and then these are like in series, and then there's resistor, another resistor. So before there was a switch here, before there was a switch there, but now we've put a resistor. Okay, there are a couple of things. What is going to happen to the overall resistance? That is how you need to think about the question. What is going to happen to the total resistance here? Because now you are increasing, you are putting another resistor here. Yeah. Okay. Okay. Okay, I want us to be practical. What was the resistance before? Okay, you would say 1 over R parallel. It's going to be 1 over R1, 1 over R2, which is 1 over 5. And then 1 over. Okay, yeah, 1 over 1. Okay, we got everything. We got R total was 4 point what? Because 4.83, well done. 4.83, yeah? It was 4.83, this one, yeah? So if this is the case, let us reason together and just make sure you understand what is happening here. So it was 4.83 with this one. But now we add something. Maybe let's assume this one is 2 ohms. Let's assume it's 2 ohms. What's going to happen? We're going to do it here. So it's going to be 1 over R parallel. You can put parallel like this. P 1 over 5. Okay. Which is 1 over 5, 1 over 3. 15. Okay, I'm just, because this one is 3 plus 2, 5. This one is 1 plus 2. 3. Okay, we're just doing a calculation here. And then we're going to have 15 divided by 5, which is 3 plus 5, which is 8 out of 15. Which means the R parallel is going to be 15 out of 8. R total is 15 out of 8. 15 out of 8 for this one, and then plus 4. Okay, so what is this? This is 32, 47 out of 8. Okay, now let's check this one. 47 divided by 8. Okay, which would be 5.875. 5.875. 875. So the R total was 4.83, and then now the R total is going to be this one here. And you're going to see, therefore, that the resistance increased. So by Ohm's law, R is V over I. So the resistance increased, then the current decreases. And therefore the power dissipated. The power dissipated. The power dissipated, therefore decreases. The power dissipated, therefore decreases. Isn't it 3 plus 2 plus 4? Yeah. 3 plus 2 plus 4. Let me check. 3 plus 2. Oh, okay. Because remember that these are in series. These two, this one and this one are in series. So, so we added 3 plus 2 is 5. Yeah, even here, the 3 plus 2 is 5. But it is therefore in parallel with this. So the 4 must be added when we have combined these parallel things. Because in this other example here, we decided to then say the 1 and the 2 ohm resistor, the 1 ohm and the 2 ohm resistor, we added them together. Okay, we added them together. We added them together. We added them together. Okay, because these 3 and 2 are in series. But this 1 and this 1, we gave it a hypothetical value. We said 2 ohms, just to give it a value so you can understand what is going to happen to the total resistance. But even if we gave it 2 ohms, then we saw that the resistance is going to increase. The total resistance is going to increase. And therefore, if the resistance increases, the current will decrease. A decrease in the current will favor a decrease in the power dissipated. But what about the reading on voltmeter V1? What would the reading on voltmeter V1 be? Let's think about this. The reading on voltmeter V1. Think about it. The reading on voltmeter V1. the reading on voltmeter V1. Okay, this one is a tricky one. It's a tricky one. But here we've already said this one decreases, yeah? But what about the reading on voltmeter V1? What's going to happen to it? Why? Okay, they even said explain. 4 marks explanation. Very well done. I'm saying very well done because it's going to increase. But the examiner then said, you know what? The examiner said they're going to give 4 marks to a student who is going to give a reason why this is going to increase. 4 marks. So let's discuss together here the 4 marks and get the 4 marks. When the voltmeter is connected, we say no, or at least very little current, through the 1 ohm branch. Okay, or if you don't want to say that, you can say that the branch with 1 ohm resistor is disabled. Which means the total resistance of the circuit increases. Total resistance of the circuit increases. Total resistance of the circuit increases. The current in circuit decreases. The current in the circuit decreases. As we've already said that, which means that V internal or what you call the internal volts, which means that V lost decreases. Therefore, the external volts increase for a constant. This is the story for a constant EMF. So we expect the EMF to be constant. So the fact that we are changing everything here, and this needs to balance, because EMF is I, which is R plus R. So like we saw in the previous question, EMF must remain the same. But the question is, if we change these components here, will it change the EMF? Well, the EMF must remain constant. If we then say that at this point, EMF is IR plus I small r, internal resistance, which is V external, and then V what? V internal, lost volts. Okay. So now let us reason together here. If EMF is constant, okay, yo, look, if EMF is constant, so EMF is constant, but what is happening here? What are we changing here? We are changing the external setup. We saw that switch S is now removed, and these are the things here. And we saw that the resistance is gonna increase when the voltmeter is connected. Right, when the voltmeter is connected, you can put a colon here like this. When the voltmeter is connected, no or very little current through the 1 ohm branch. Because it said this has very high resistance, so it means that this one will override this one, because this V2 is like a big resistor in terms of resistance. So very little current through the branch with the 1 ohm resistor. So the branch with 1 ohm resistor is disabled. So by virtue of this one here, it's going to be the biggest resistance, in which case it's going to disable this one. So the branch with 1 ohm resistor is going to be disabled. The total resistance of the circuit increases. We've seen that the total resistance of the circuit increases. Current in circuit decreases. The current in the circuit decreases. And we saw that that is by dint of Ohm's law. The resistance increases and the current goes down. V internal. V internal, or the internal volts, or the lost volts decreases. Okay, so if we then say that the total resistance increases, the current in the circuit decreases. So this is very interesting. So the V internal, or the lost volts, decreases. So we have the lost volts decreases. Therefore, the external volts must increase, because the EMF must be constant. The EMF must be constant. The current in the circuit decreases, but now the V internal decreases. When the V internal decreases, it means that the external volts have to increase for a constant EMF. Okay, this gives us the justification for this part. That we have to explain the answer to 8.4.2. We have to explain why the reading indeed increases there. In 8.4.2, the reading increases. And the reading increases because of these reasons. These reasons were stated. That if you put a big voltmeter here, a very high resistance voltmeter, what it does is it disables this one. So this is very small, this 1 ohm resistor, meaning it's negligible relative to the V2. When the voltmeter is connected, you can say there is no or very little current through the branch with 1 ohm resistor. There's very little current. through the branch with 1 ohm resistor, because this one is blocking everything. Very high resistance. Because of the very high resistance here in V2, it means that there's very little current that is going to pass through this. Meaning this one is disabled because this one is blocking all the current. This V2 is blocking all the current because it's a very high resistance voltmeter. So the total resistance of the circuit increases. So this V2, we did an example to show that the total resistance is going to increase. We actually said it's maybe 2 ohms, 2 ohms. You'll see that it's going to therefore increase the total resistance of the circuit. Now, the current in circuit decreases. So because the total resistance increases, then the current will go down. Resistance increases, the current will go down. So the current in the circuit decreases when the resistance increases. The overall resistance externally increases, therefore the current in the circuit decreases. Okay. Okay, good. Let's give the homework, please. Thank you so much. Yeah, so and in the end, then we have V lost, the lost volts of V internal. V internal or the lost volts decrease, and then for the external circuit, the V external, the external volts increase for constant EMF. If one decreases, the other one must increase because EMF must be constant. The EMF does not change by dint of many things there. Right. So this one is the homework. It's the home activity. I'm just going to read through it and then we're going to give to you. In the circuit below, a battery of unknown EMF and an internal resistance of 0.5 ohms is connected to 2 resistors of 4 ohms and 8 ohms. 4 ohms and 8 ohms. I'm just reading so that you can forward the video to the end. You can forward the video to the end and just see this one. It's not going to be very long. And a resistor R of unknown resistance. This resistor R is of unknown resistance. Ignore the resistance of the connecting wires. The 3 external resistors are ohmic. Okay, so this is very interesting. They're ohmic. Explain the meaning of the term ohmic conductor. Okay, the 3 external resistors are ohmic. The 3 external resistors are what? Are ohmic. 1, 2, 3, they are ohmic. Explain the term ohmic conductor for 2 marks. Let's check another exercise. Okay, then we're going to do these calculations here. When switch S is open, like this, voltmeter V1 reads 3.2 volts. Okay, this one, V1 is going to read 3.2 volts. Calculate the current through the battery. We need to find the current through the battery, and then we would have to find the EMF of the battery. The current through the battery is 3 marks, and the EMF of the battery is 4 marks there. All right, I think it was awesome having this discussion on electrical circuits. Obviously, you actually have noted a couple of things you need to note for purposes of exams. Right, so, yeah. Until next time, it was awesome. Take care. And yeah, let me see what they were saying. All right, thanks so much, Noah. All the best. We'll talk then until next time. Take care and goodbye. Bye, Noah. Goodbye. Bye.